Hey class, Mr. Moynihan here to answer the age-old question, why is it called tangent? Because in geometry you learned that something like this is a line tangent to a circle because it touches once and only once. But then you learn in trigonometry or other parts of right triangle geometry that tangent is also this ratio of opposite over adjacent. The question is, why is it also called tangent? That's a very common question. I thought I'd answer it for you. So recall that in trigonometry you're dealing with the ratio of lengths in a right triangle, and the right triangle is considered to have, in a unit circle at least, which is the conceptualization of trigonometry, a radius length of 1, hence the name unit circle, a single unit. So if you have a radius of 1, then that makes things quite easy because your opposite length is considered the sine of x, because sine of x would equal opposite over hypotenuse, opposite over 1, so sine is your opposite leg. And the adjacent leg is considered the cosine for adjacent over hypotenuse. So this just makes the SOHCAHTOA rules work out nicely when you have 1 here as the hypotenuse. So a question that emerged in really early geometry and trigonometry when this was developed in ancient times was, how long is a line tangent, which I didn't draw very well, maybe this is better, tangent to the circle, sort of in this configuration. If you have that same angle here, then if you extend this further out, then what would this length right here be? The length of the tangent, in a sense, right? Well, what you should notice, if you look very carefully here, you should notice you have a big right triangle here, and a big, smaller right triangle, of course, the original one. And since a radius and a tangent meet each other at 90 degrees, that's provable from geometry, and then, of course, right triangle trigonometry, that's also 90 degrees, they both share this angle theta or x, we're calling it x here, so by angle-angle similarity, these two triangles are similar. And because they're similar, we can come up with a proportion. So I've redrawn it on the next slide. The basic question is, what is the length of this segment here, which is tangent to the circle? Well, because of similar triangles, let me kind of simplify the picture here so you can see it a bit better. Here you have a radius of 1. I didn't draw this very well. Let me do a better job of drawing it that somewhat to scale. There we go. Okay. Here you have the unit circle radius of 1, and we already have the sine and cosines from before, so that would be sine, and this would be cosine. And the question is, what is the length of this thing right here? Well, the key realization is that because this is a circle, and the hypotenuse of the small right triangle is 1, but this is also 1 right here, because it's also a radius. So this length right here is also 1. So our proportion, if we match up matching parts, would be this. Looking at the big triangle, the opposite side divided by the adjacent side, so the question mark and 1 are in proportion. Because they're similar, they're proportional to the small triangle, its opposite side, its opposite side and its adjacent side. So basically matching corresponding parts together so that they make proportions because they're similar triangles. So multiply both sides of your equation by 1, and the unknown side is equal to sine of x over cosine of x. And since this unknown side is tangent to the circle, we say that this ratio is therefore tangent of x. Furthermore, sine, we know from SOHCAHTOA, is opposite over hypotenuse. And cosine, furthermore, is adjacent over hypotenuse. So if you simplify this by some simple fraction multiplication and division, what you eventually get is opposite over adjacent. So opposite over adjacent gives you the same as sine over cosine, which in turn is the same as tangent over x, so we call opposite over adjacent tangent because it's the length of this tangent segment. There's some math history for you.